In the realm of theoretical physics, string theory stands as a captivating development that has sparked both academic and media interest. It's seen as a potential answer to some of the most profound questions in fundamental physics, to the extent that it is considered by some as a candidate for a theory of everything. String theory, more accurately described as a theoretical framework, offers a radically different perspective on the universe's most fundamental aspects. String theories propose that the point-like particles of particle physics, such as leptons or quarks, are actually one-dimensional strings. These strings, incredibly small and existing at the Planck length scale, can be either open or closed. The unique characteristic of these strings is their vibrational states. The way these strings vibrate determines the properties of the particles they represent at a larger scale. However, for the mathematics behind various string theories to be consistent, additional dimensions are required beyond our familiar 3 spatial and 1 temporal dimension. Some string theories, for instance, posit that there are as many as 27 different dimensions to our universe. The notion of these extra dimensions can be challenging to comprehend, as they are not observable in our everyday experiences. The explanation often used is the analogy of a pole with tiny objects that can move not only up and down, but also around its circumference. To an observer at a distance, only the movement along the length of the pole, 1 dimension, is noticeable, not the movement around its circumference. This is akin to how extra dimensions in string theory are envisioned. They're curled up so small that they're not perceptible at our scale. One of the most significant accomplishments of string theory is its ability to incorporate quantum gravity, a feat that has eluded many quantum theories. Gravity, as described by Einstein's theory of general relativity, often conflicts with the principles of quantum physics. This is largely because gravity involves the geometry of space-time itself, which requires precise measurements of distance, measurements that become problematic at the quantum level due to the Heisenberg uncertainty principle. String theory elegantly addresses this by introducing the concept of gravitons, hypothetical particles that mediate the force of gravity, thus allowing gravitational interactions to be described in the language of quantum physics. The search for a theory of everything is essentially a quest for a unified framework that encompasses all known physical phenomena. Currently, the standard model of particle physics describes most of the known universe, but it fails to incorporate gravity. A true theory of everything would seamlessly merge gravity with the standard model. Here, supersymmetry offers a promising avenue. Supersymmetry is a principle that treats forces and matter on an equal footing and predicts the existence of superpartners for every known elementary particle. These superpartners are theorized to be the opposite of their regular counterparts, for example, bosons for fermions. While elegant and attractive, supersymmetry faces criticism, primarily because no superpartner particles have yet been observed. String theory and supersymmetry have given rise to superstring theories, each proposing 10 total dimensions and providing compelling explanations for various quantum phenomena. However, these theories appear to be only pieces of a larger puzzle until American physicist Edward Witten proposed that they might be aspects of a more fundamental theory, known as M-theory. Presented at a conference in 1995, M-theory suggests that the various string theories might not be distinct, rather interconnected parts of a broader framework. M-theory, which stands for membrane, or is sometimes jokingly referred to as mystery or magic, posits an 11-dimensional universe. It expands the concept of one-dimensional strings to include higher-dimensional objects called p-branes. These p-branes range from 0-dimensional points to 9-dimensional entities, challenging our conventional understanding of dimensions and their interactions. A significant implication of M-theory is the possibility of a multiverse, as it allows for an astronomical number of different universes, each potentially having its own set of physical laws. This idea stems from the understanding that the shape of the extra dimensions in M-theory dictates the physical constants and interactions in our universe. As such, different shapes of these extra dimensions could lead to entirely different universes with their unique laws of nature. The concept of a multiverse, with possibly 10 to the 500th power different universes, has further fueled the fascination with M-theory. Yet, despite its potential, M-theory remains largely theoretical and speculative. Its confirmation through observational evidence would be a monumental stride in our understanding of the cosmos. The quest to verify M-theory and explore its implications continues to drive cutting-edge research in theoretical physics, with the hope of unveiling the mysteries of our universe and possibly many others.